Welcome to Digital Education Hub. Now today's topic is set theory. So this is the extension of the previous video where we have learned the basic definition of set theory along with the various ways of representation and the types of set. Now in today's video we are going to learn the operations of set, which operations we can perform, and the set identities. So let's continue with this. Before starting, I would like to request you, if you like this video, please like, comment and subscribe to the channel. So let's start. Suppose we have this set of colors and we are picking any three primary colors. So we are picking two groups in this way, that is two set. So this triangle shows the mixable color range, and with this way we are selecting the two set. And now here, so the first set can be called as a monitor, that is monitor gamut, and that is M. The printer gamut, that is P. And in this one, so we can see that operations, various operations which we can perform. Now here the first operation is union operation. So union operation is nothing but it says that it contains all the elements which is present in either of the set. So here this that graphically it can be shown like this one. That is, this is the reason where this union is basically we are talking about. And then we have this symbol, union symbol is denoted as this U, and so we can say that this C is equal to M union P. Now how these operations can be denoted via Venn diagram. So we have a universal set, and along with that universal set we have the two set A and B, and this is the way union can be represented, that is covering either the element should be present in either set A or set B. So we can say that this is the whole reason with the shaded part. Now the formal definition of the union says that A union B is equal to X, such that X is the element of A or X is the element of B. So it is either present in A or B. Okay, both can also be taken. So for example, you have two set like 1, 2, 3 and 3, 4, 5. So what is the union of 1, 2, 3 and 3, 4, 5? So we can say that writing all the elements of set 1 and set 2 without repeating the elements. So 1, 2, 3, 4, 5. So the definition says that it is a set of well-defined objects. Okay, so the repetitions are not allowed, or it should not be there. Then the second case, you can see that there is another example, New Delhi, Mumbai, and there is another set 3, 4. Since nothing is common, you don't need to worry about anything. You can just write down all the elements and that would create the union set. And the last example, the set along the take union with a null set. There is a set A and you are taking the union with null set, that will result in set A itself. So here 1, 2 with union with a null set, that would result in 1, 2 itself. So with this one we can create the various properties of union operation. So the first property is A union null, that is set A union with the null set, and this can be called as identity law. That A union with the universal set is nothing but universal set itself. So here, since universal set is dominating, and this will be called as a domination law. Then if you take the union of set A with itself, then the result would be set A itself, and this is called as the idempotent law. Suppose if I can say that A union B is equal to B union A, if the result is remains same, then we can say that it is a commutative law. The next property is basically A union B union C. When I'm saying this one, so association of the terms, I can say that the terms associated, like in this one we can say that here the association of B and C is there. Here A can be associated with B, but the result remains same, and if it is the case, we can say that it is following the associative law. The next operation we can perform is intersection. So intersection also follows almost all the laws. So here the intersection can be called as, like, it contains all the elements in both the sets, like whichever is present in both the sets, that would be the part of that intersection. So here diagrammatically we can say this one. So it is the common region of set M and P. So symbolically we can say that this is the case C is equal to M intersection P. So this is C equal to M intersection P, and now so we have universal set along with the two set. So this shaded region will be the intersection, the common region. Now the mathematical way of representation is, that is A intersection B can be called as X such that X is element of A and X is also element of B. Let's see the example. So the first set is 1 2 3, the second set is 3 4 5. So the intersection means that common element, so the common element is 3. So here in the next example, nothing is common between New Delhi, Mumbai and 3 4. So we can say that the result would be null. Now the next example, 1 2 intersection with the null. So here, since we are taking the intersection with a null set, and the result would be same, that is null only. So whenever we are trying to find out the intersection with an empty set, then that would result in an empty set only. Now, so the properties basically of this intersection operation is, if I'm taking intersection of A and universal set, then it will result in set A itself. This will be called as the identity law, since it is maintaining the identity of the set. Next, if I am taking the intersection of A with null set, in this case the result would be null. So intersection of any set with the null set is going to result in null. This is the dominance law. A intersection with A, that is set intersection of set A with itself, is going to result in set A itself, that is the same element will be common, and this is called as the idempotent law. The same commutative law and the distributive law, associative law, is applicable over here also. Okay, now the next operation which we can perform is a disjoint. So what do you mean by disjoint? So disjoint means that they don't have any element as a common one. So here we have the two representation, this one and the next this one. So they don't have anything common between them, that is their intersection is an empty set. So we can say that this graph, they are like intersection is null set. So for example, even numbers, that is set of even numbers and set of odd numbers, nothing is common between even number and the odd number. So we can say that they are basically disjoint set. So how this Venn diagram can be utilized for representation? So this is the way basically we have a universal set and we have the two set representation, and since you can see that there is nothing common between them, so we can say that these are the disjoint sets. In the formal definition, we can say that the way of representation is, we will define that A intersection B is equal to null, then we can say that A and B both are disjoint sets. For example, the first set 1 2 3 is there, so second set is 3 4 5. They are not disjoint because there is a common element, that is 3. They are not equal to, the intersection is not null. Okay, so in the second case it can be called as disjoint because nothing is common between them, the intersection is null. And here in the third case 1 2 and intersection with the null. So you already seen that the set, any set, intersection with any set, intersection of null set with any set is going to result in a null set only. That is, since the result is null, intersection result is null, and that would be called as both the sets are disjoint. Intersection of the intersection of null and null would result in a disjoint set only because nothing is common between them. Okay, no elements are present, and because of that it will be a disjoint set. The fourth operation which we can perform with the set is difference. So the difference of two set is removing the elements in one set that are not in the other, like the elements in one set that are not in the other. So suppose we have this particular set M and set P. So M minus P will stand as removing the elements which are present in M, okay, so which is also present in P. So here, since this region, the central part was present in P, so M minus P will stand for this one. Okay, so C is equal to M minus P. So you can see this one, C is equal to M minus P. Okay, now here this is the case. So let's see that the next case, if I can say that C is equal to P minus M also. So here we will see that one representation. So C is equal to P minus M. So here this P is there. So P minus M means P, from P subtract the common reason. PC equal to P minus M. The difference can be represented with a Venn diagram through this way, that is B minus A. Suppose if I am having set B and set A, then B minus A can be represented with, take the B set, take this set, and from this you remove the common elements which is also present in set B. Common elements of A which is also present in set B. So remove that one. So this would be the remaining part. So this is the answer, B minus A. Here we can say that another case A minus B. So A minus B can be given like this one. So considering the set A and removing the common elements which is also present in B. So let's see the formal definition. The formal definition says that A minus B is equal to X, such that X is an element of A and X is not an element of B. Okay. So it also can be defined as A minus B is equal to A intersection with B complement. That is, A is present and B not present. For example, we see that. For example, if we have the set 1 as 1, 2, 3 and the second set as 3, 4, 5, then if you subtract, so what you have to do is you just write down all the elements of set 1 except the common value, okay, the intersection value. So we can write down 1, 2, and since 3 is common between both of them, so you can just remove that value. The next case is, just try to find out New Delhi, Mumbai, this is the first set, minus the another set. So you write down the elements of the first set except the common element. So nothing is common between the set 1 and set 2. So here we can say that the result would be New Delhi, Mumbai, and similarly 1, 2 minus null is going to result in 1, 2. So the set operation, the next set operation will be called as a symmetric differences. A symmetric difference basically is all the elements in either set but not in both. So which is present in either of the set but not present in both the sets. Okay, so this can be the case. So we are removing the common reason, that is, which is present, the element which is present in both of them, we are removing that one. So this is the reason for symmetric differences. Okay, so C is equal to M XORed with P. So this is the symmetric difference symbol. Okay, so Venn diagram through, that can be like we are just removing. So if we are using the Venn diagram representation, in the Venn diagram representation, this would be like covering this region with and this region without this section, that is the common section. So that would be the representation. And then the formal definition of the symmetric differences can be given as, that is, A x symmetric differences with the B is equal to X such that X is belongs to A, that is, X is the element of A or X is the element of B, and X is not an element of intersection A and B. So it is not common to them, but it is either present in A or B. So this can be also called as A union B minus A intersection B. Okay, so let's see the example. So in the first case, we have the set 1, 2, 3. The second set is 3, 4, 5. So while XORing, what we are going to do is we are going to remove the common elements. So if something is common between them, that would be removed, and write down all the other elements. So 1 2 3 3 4 5, the 3 is common between both the sets, so we will remove that value and the result would be 1 2 4 5. So this is the case. And now in the second case, New Delhi, Mumbai and 3 and 4, here the symmetric differences result would be, you write down all the elements without the common element. Same goes with the 1 comma 2, symmetric differences with the null. So here that would result would be 1 comma 2. The next operation which we can perform on the set is complement set. A complement of a set is all the elements that are not present in the given set. So suppose if I'm talking about M, so except the region of M, consider the other elements. So other than M part. So M bar means other than M. So here I can say that P bar or M bar. So for P bar, we can say that except the region of P, considering every other element. Okay. So through a Venn diagram representation, A bar can be given as this one, like considering every other element except these set element, set A element, and same for B bar also. Now what is the formal definition? The formal definition says that A complement is equal to X such that X is not a member of set A. So here it also can be represented as U minus A, that is universal set minus A. For example, we see that, suppose consider the universal set as a integers, set of integers. So here if I am having one set as 1 2 3, and if I am taking the bar of that, it means that from the set of integers, you remove 1 comma 2 comma 3. So this can be represented like this with ellipses. So here that representation works. What are the properties of complement set? So on a particular set we can take a double complement. So complement of complement, that will result in a original set A. Okay, so this is called as the complementation law. Then we have A union with the, that is set A with union with its bar, its complement, and that would result in universal set. This is called as the complement law. The first one is called as the double complement. Similarly, if I am taking set A intersection with its complement, and then that would result in a null, because nothing is going to be common between set A and its bar, its complement. Okay, this is also called as the complement law. Now we have the set identity concept. Set identity is basically the basic laws how this operation works. We already seen some of them, so we can utilize some of the concept like logical equivalences. Okay, so here the union, intersection, that null and that universal set can be replaced with its equivalent logical symbols, and that can be disjunction, conjunction, false, true. Okay, so we are going to use that one to simplify the set identities. To understand the set identities, there is one law in the set identities, and that is called as DeMorgan's law. The DeMorgan's law says that the complement of intersection of two set is equal to union of complement of two sets. Or there is another statement, complement of union of two set, which is equal to intersection of complement of two set. So this is the DeMorgan's law. Okay, we can verify this particular DeMorgan's law or this any set identities through 4 methods. Okay, so to prove any set identity, we can utilize the 4 methods, and that 4 methods are basically this one, the basic set identities. We can use the basic set identities to prove them, or we can utilize a membership table, or we can prove each set is a subset of each other, and by proving that we will prove that particular equation. Or the fourth way is we can build this set that we can utilize the set builder notation and logical equivalences to prove them. So we are going to study this particular set identity in the next session, in the previous video, and till then we can wind up this particular session. So this would be the part. Thank you. Once again, I would like to request you that if you like this video, please like, comment and share, subscribe to this particular channel. Thank you.